Hello. All right, so welcome to the session 7D, which is one of the last sessions before the banquet. So graph neural networks. So I'm Xulong Tang from University of Pittsburgh. So we have four very interesting work present here. So our first speaker is Yufeng Wang, and he graduated with his master in 2023 from UIUC. And his research focuses on temporal graph neural networks. Today, he will talk about the tool, basically how to use the implementation of a graph neural network and how to build a programming framework for the graph neural models.
Hello, I'll be presenting our work on TGLite, which is a lightweight framework for programming continuous time temporal graph neural networks. By lightweight, we mean that it provides a core set of abstractions and operators that users can use as building blocks to implement their models. In this talk, I'll go over the motivation behind TGLite, how it compares to existing work. I'll describe T-blocks, which is one of our main abstractions, and we'll see that implementations using TGLite can achieve speedups for both training and inference. Before all that, though, we have to learn a little bit about how machine learning on temporal graphs work. So compared to a typical graph with a static set of nodes and edges, temporal graphs are dynamic and changes over time. For example, you might have new users in a social network or new transactions in a financial network. These temporal graphs can be represented in two different ways. One is discrete time graphs, where we take a snapshot of the graph at certain time intervals. The other is continuous time graph, where we have a stream of graph changes, such as adding new edges. Here, these snapshots are effectively static graphs, and overall they capture very little time information, whereas continuous time graphs have richer time information with these explicit timestamps. And time information can be crucial for certain applications, so we're much more interested in these continuous time graphs. As for temporal GNNs, these jointly learn on the graph structure and time information of the temporal graphs. And a common way to do this is the message passing pattern. There's two main steps to it. One is we look at our neighbors and select ones that have an edge timestamp less than some time t. And we can do this 3 hops. Then we collect node and time features of each neighbor, aggregate them, and then pass that along all the way back to the starting node. Aggregation can be done by concatenating the features and then taking the sum over neighbors, or taking a mean, or using something more complex like self-attention from transformers. So the question we're interested in is, how does a researcher or programmer go about implementing these models? Let's look at a model called TGAT. This is this network architecture for one layer. Looks somewhat complex, but at a high level, it first samples some recent neighbors. Aggregate by concatenating self-attention, just like what we saw earlier. Pass it along to the next layer and repeat. If we examine its reference implementation done in Python and PyTorch, what you see is that first, we need a way to represent the graph and sample neighbors. So we have these very ad hoc data structures and utilities. Then you notice that because we're doing message passing over multiple layers, it ends up being a somewhat tricky recursive implementation. Recent research shows there are these redundancy-based optimizations for these models. So we can implement those here. However, these require pre and post processing steps. So now our main logic is sandwiched between these steps, and the programmer has to manage all of these bookkeeping. Not to mention that for efficiency, you might want to go down to the C++ and systems level. However, researchers might not have that kind of knowledge or the time for that sort of effort. So perhaps using a framework will help us out here. There's popular frameworks for static graphs. These don't directly support temporal graphs, but they do bring something to the table. In the DGL library, there are these message flow graphs. These MSG objects could be used to represent a set of nodes and their sampled neighbors. This is nice in that it turns this whole recursive flow into an iterative one that's easier to understand. So, however, the programmer still needs to implement all the time-related pieces themselves. If we survey prior work for temporal graphs, there are ones like Dynagraph that have nice optimizations for discrete time graphs, but the only one we're aware of that supports continuous time graphs is TGL. Unfortunately, it does not expose any sort of programming interface and lacks certain optimizations, so it'll be difficult for users to explore new model designs or implement more efficient ones. And this brings us to our TGLite framework. Here's a little example of what it looks like to use TGLite. So first, the programmer will import our library. Our framework works with PyTorch, so the user can use all the things that they like from PyTorch to start the implementation. For the actual computations, they will use our abstractions and operators to construct those flows. Let's revisit the TGAP example. If we implement this using TGLite, then we get access to a library with things tailored to temporal graphs, such as this tgraph object for storing training data, and this tsampler for sampling recent neighbors. We get to use what we call T-blocks and operate on them using built-in operators, such as to sample and aggregate from neighbors. And applying optimizations is as simple as adding 1 or 2 lines of code. So these T-block abstraction is at the heart of our framework, and it allows us to define many different operations and optimizations. So a T-block essentially captures the one-hop dependency between a set of targets that we're working with and their temporal neighbors. For static graphs, we have these MFG objects. Now for temporal graphs, we have these T-block objects with first-class support for time-related operations. If we zoom in on one of these blocks, it looks something like this internally. There's 3 key distinguishing factors here about T-blocks. So first, we can construct a double-linked list structure out of these blocks, and this allows us to explicitly capture the multi-hop relationships often seen with these TGNN models. Second, we can incrementally build and manipulate the mapping between these targets and these neighbors. Lastly, we have this mechanism for registering functions to run later, which we call hooks, and that can come in handy for scheduling post-processing steps. Let's actually take a look at how these design choices help with defining some of the operators. So one common thing we want to do is multi-hop aggregation. So we have this aggregate operator that takes a function and applies it to multiple blocks. Internally, it will traverse this list of blocks that we have using the attributes like previous and next. And any bookkeeping needed to pass data from one hop to another is handled internally. For optimizations, we have this preload operator that will efficiently fetch feature data using pinned memory, which is allocated and managed by the framework. So the programmer doesn't have to really sort of worry about that. And internally, this will also traverse the list of blocks. Lastly, for redundancy-based optimizations, such as deduplication, those are defined as yet another operator in our framework. To understand this one, let's look at a quick example. So suppose we have 3 target nodes here with their corresponding timestamps. We can sample for their neighbors, but you'll notice that there is a duplicate here with the same node and timestamp. And that means we'll sample the same neighbors and perform the same calculations. That takes up extra storage and performs redundant computations. Instead, what we can do is filter out these duplicates by matching up the nodes and timestamps, perform our computation as usual, and then undo this filtering by duplicating the outputs. So semantically, we're doing the same thing and getting the same results, but doing less work. So for this operator, internally, it will manipulate the mapping of the T-block and register a hook to do this post-processing step. Now, lastly, we'll look at some experimental results. So we evaluated our work by implementing 4 different models from the literature and compared to the TGL framework using 4 different data sets. So these data sets are rather small and their feature data fits entirely on the GPU device. So we'll call this the all-on-GPU case. But as temporal data sets grow ever larger, that will always be the case. So we also examine a scenario where the training data is on the CPU host and moved to the GPU. For training, we measured the average epoch running time. So here, lower will be better. We show results for 2 of the data sets, and more can be found in our paper. Across the board, we see that we're able to either match or outperform the other framework. And a big part of that is we're able to tap into these redundancy optimizations. As for the other scenario, it will be important to optimize for the data movement here, which we do in TGLite, and that brings the speed up to as much as 3x. And the user can tap into this using the preload operator. Next, for inference results, we show results for the other two data sets here as relative runtime speedup. So here, higher will be better. We see we also get speedups of 3 to 4x. To get more insight into this, we conducted an ablation study of these redundancy optimizations we used by applying only one of each. Before applying any of them, we see that there can be some overheads. We found this was due to using external kernel library calls, so that's something we can improve upon. But we can get some speedups using the preload operator in this other case here. With applying the optimizations, we get much better speedups, with deduplication and caching being the better ones, as those help minimize expensive calculations such as self-attention. And as we mentioned earlier, these optimizations are semantic preserving, so they'll retain the accuracy of the models. Lastly, we also these operators, and the user is allowed to sort of choose to use a cat.
Makes sense, makes sense. Thank you.
Any other questions? Yeah, I do want just to ask one from my curiosity. So the performance seems, get very good performance gains, and I really appreciate this T-block abstraction, which would be very good to benefit the entire community for such research. So I'm wondering that this improvement, are they model dependent or independent? For example, if I change a different structure graph neural network model, will that preserve the same performance improvement?
That's a very good question. So I think it will be data set dependent because the optimizations we do currently is based on redundancies, trying to eliminate redundant computations. So opportunities for redundancies arise based on sort of the data set behavior. So for example, if you have a data set of like a social network of users, it will depend on like how active are users in your graph. So it will certainly depend.
That's great. Thank you for the answer. So let's thank our speaker again. So we'll be for the next steps.
Yes. Okay, thank you. We can send the slides to you in email.
No, I don't need to.
Okay. It's good. It's flash. Okay, great.
I guess it's good. All right. So let's get to the second presentation. So our second presenter is Hongwu Peng. Hongwu Peng is a PhD candidate at the University of Connecticut. His research interests include machine learning systems, efficient machine learning, secure and trustworthy machine learning, and generative AI. So,
Hi, hello. So my today's presentation topic is MaxK-GNN, extremely fast GPU kernel design for accelerating graph neural network training. So the graph neural network is being widely used in different applications, including social network analysis, point cloud, and molecular graph and power grid. And the graph neural network consists of node and links to form complex networks, and it has a capability of node, link, and graph level predictions. And it demonstrates versatility in analysis and forecasting. So, but there remains one of the major bottleneck in the graph neural network training system. So, which is sparse matrix multiplication, the sparse matrix multiplication operation. So, this point out a question: can we achieve a high accuracy and high hardware sparsity to accelerate this sparse matrix multiplication? And then in this way, we need to rethink the specification method. So there are old literatures which is talking about the sparse training, which specify the weight, but the weight and feature multiplication only composed of a few percent of the overall training time in the graph neural network training. And then there are other ways of dropout, which is a feature specification, but the dropout is extremely irregular and hardware unfriendly. And then this brings to the nonlinearity design. So can we utilize some of the hardware-friendly nonlinearity? So there are examples of using C-loop for the nonlinearity. C-loop will not introduce any of the sparsity. And then there is some of the nonlinearity which is like a ReLU. It will introduce a sparsity, but the sparsity is extremely irregular and is very hard to utilize in the hardware. And thus we brought out the node-wise MaxK. So this is one of the nonlinearity which we can utilize. So the nonlinearity is effectively selecting the maximum K value out of each of the node. And then this will also be served as one of the nonlinearity in the network. So because we are in this kind of nonlinearity, we can get the node balanced or the row balanced sparsity, and it will be friendly for the hardware to do the acceleration. Then we further prove that this kind of MaxK nonlinearity is a universal approximator. So universal approximator, which is similar to ReLU, means that with two layers of the multi-layer perception, with this kind of nonlinearity, we can approximate any of the function up to any of the granularity, with given number of hidden layers, hidden dimensions. So the detail of the proof can be found in the paper. And then here is the training data flow of our MaxK-GNN training system. So in the MaxK-GNN training system, we'll have a previous layers feature coming in and then pass through one with the linear layer. And then we'll use MaxK nonlinearity to introduce the specified feature matrix, which will be stored in the column balanced sparse row format. And then we use the sparse data and sparse index to store this kind of matrix. And then in this way, we use for the forward, the original SPMM will be transferred into the SPGM, and the backward will be transported into the sampled SPMM. And then we have developed the corresponding kernel support to do this SPGM and then the sampled SPMM operations. So for the forward, we use row as product for the forward SPGM for SPGN computation. And then for the backward, we utilize outer product for the sampled SPM computation. So the reason why we use this kind of format, we are introducing the later kernel design. So this is a forward SPGN. So in the forward SPGN, we are iterated through each row of the left side matrix, which is effectively the adjacent matrix. And then we are form a warp partition for each of the row. And then in this example, we include we use each of the warp to process 3 non-zeros in the warp partition. And then for for each of the world partition, we will initialize the buffer in the shared memory to do non-zero and vector multiplication. And then if you look into the equation, we found out the output is actually sparsely accumulated, but this sparsely accumulated pattern will be happening in the shared memory. So it is much more efficient than sparse accumulation in the global memory. So zero plus vector multiplication, and then after we finish the multiplication, we'll accumulate the buffer result into the global memory using the atomic adding. And then for the next row, because it will have five non-zeros, and then for each of the world partition, we'll have for each of the world partition, it will be in charge of computing three non-zeros, and then we'll firstly compute the first three non-zeros using this warp, and then after this is done, we'll use the next warp to compute the next world partition, and then after atomic accumulation into the global memory. So and this is and the operation is the same for the third row. And then that's all for the SPGN kernel. And then in the backward sampled SPM kernel. So because in the sampled SPM kernel, our input is actually dense and the output is actually specified. So it's like we already know the output sparsity pattern, and then we want to reduce the computation and then only compute the corresponding element in the output, which we need to develop outer product-based sample SPGM for each of the row in the right-hand side matrix. We firstly we need to firstly load it into the shared memory, and then after that we will form M threads within a warp, and then for each of the non-zero which correspond to the column of the addition matrix, we use a value vector fetch the specified value from the shared memory. Fetching, we can and then we are iterate through each of the row of the right some of this testing, and then we found out normally we can have a compared to MaxK, right? So we are also have the latency of that compared to the ReLU baseline, we also have a effective speed up like probably 1.5 times speed up. So even if we are using the original time dimension as a 64 around that value. Okay, thank you.
Any other question? I think we have come to another one question if anyone want to ask.
So when you talk about sparsity, does it include the sampling things? I mean, GraphStage uses a sampling, right?
So in our experiment, we just use a full batch training as this benchmark. So we didn't use any of the sampler. So we just use
GraphStage uses a sampling, right? It is basically feature embed. I mean, sampling.
The original GraphStage use a sampler, but in our testing, we just keep the GraphStage layers the same as the sampling GraphStage layers, but we don't use any of the sampling. We just use a full batch training. So just to make the result to be consistent with other networks.
Okay.
All right, let's thank our speakers again. And our next speaker is Quinn Wu. Quinn is currently a fifth-year PhD student at UIUC, advised by Professor Wang Wu. His research interests lie in the compilers and libraries for GPUs and parallel computer architecture. He has contributed several very impactful projects, including PyTorch Direct, Pylog, and the ML ASPLOS Tensor Direct.
Great. All right. Okay. Thank you for the introduction. It's my honor today to present our Hector work for relational graph neural networks. I'll start with the application and example of relational graph neural networks. There have been wide adoption of relational graph neural networks in graph representation learning these days. RGNNs are kind of variants of GNN. GNN is a type of deep learning model that does forward propagation according to the sparse adjacency matrix of the input graph data. It takes the graph as the input and outputs dense vector of nodes. Relational different types into consideration and assign weights to each of the which is one variance of RGNN. The results are feature vectors of each node. The input is the embedding of each node. Embedding is vectors produced from the existing information describing the node. For example, it could be a vector learned from the description of the product. After this all gets layer, the output feature of each node now incorporates the information from those nodes with edges to it. There are two stages in a graph neural network. Let's start from the end to the beginning. The second stage is node aggregation. For products 1, for example, the messages on edge, product 0 to product 1, and person 2 being interested in product 1 are aggregated in a weighted manner. The messages and the scalar here are both generated in the first stage. We call these scalars attention. They are produced by the model that emphasizes or diminishes the messages. For product 1, we need to calculate the attention and message on both edges in the first stage, the message generation stage. To compute that message, the RGET model applies a type A linear layer to the source node features. The attention is computed through a function with source node feature, destination node feature, and edge type as arguments. It's a procedure that takes in both the source node embedding, destination node embedding, and multiple weights according to the edge type. Similar to the example of product 1, the RGET layer will apply the same procedures to all the nodes. There are two main challenges in RGNN execution. The first one is the inherent memory intensiveness. Here we show the inference trace breakdown of the most performant existing compiler, Graphila.
We execute a model to produce node features while two different models on two datasets. Heterogeneous graph transformer, HGT, is a more compute-intensive model. MuTag is a smaller graph. As we can see, Graphiler spends significant portions of the time in indexing and copying. These are large amounts of data movements to prepare for highly specialized kernels like matrix multiply. A lot of the computation, not matrix multiply. They are categorized as other compute and involve vector inner products and matrix vector multiply as examples. They are usually memory intensive. Second, lack of TensorView in PyTorch programming interface causes redundant data copy. Let's take a look at message generation, for example, while the same issue exists in edge attention calculation. In the RGAT model, to generate message, we need to do a matrix multiply on each edge. A typical way of doing that is to use the batch matrix multiply API provided by PyTorch. Matrix multiply on each edge is a sample in the batch matrix multiply. Before the batch matrix multiply, the weight tensor has to be materialized, causing redundant weight copy. To recap, we have two challenges in RGNN execution. To systematically address these challenges, we propose the Hector two-level IR and code generation framework. To mitigate the inherent memory intensiveness, Hector captures the key properties of RGNN models and opportunities to reduce memory excesses in inter-operator scheduling and materialization. To avoid weight replication, Hector captures the model semantics and generates code with flexible data access schemes to eliminate redundant data copy. Next, I will illustrate the Hector workflow and the two optimizations. My approach is for throwing these complicated proxies in front of you, but I will walk through this one by one. So here, this is basically the Hector workflow and software architecture. I will walk through these blocks one by one by using an example of edgewise type linear. For convenience, we provide TGLite APIs at the programming interface. Code generation will handle decorated functions. The API call is first transpiled to inter-operator level IR, which extends the Python language to express the model semantic. The code is then lowered to the intra-operator level. IR at this level specifies how CUDA kernel will be generated. Here, it specifies the edgewise type linear should be lowered to a gem kernel and specifies the loading and storing schemes. The code generator then generates the CUDA kernel based on the gem template, compile it, and register it in PyTorch runtime. PyTorch runtime will then use the CUDA kernel in model execution. Let's see how the inter-operator level IR works. Inter-operator level IR defines the model semantics as a sequence of operators in a manner that abstracts away the tensor layouts. Notice that here we use a different graph than model citations. The nodes in the graphs are papers, authors, and institutes. Edges mean relationships such as a paper citing another paper and one author belonging to an institute. In RGAT model, during edge message generation, there is matrix multiply on each edge. To express that at the inter-operator level, what we do is to create an edgewise iteration and specify the matrix multiply in Python grammar. We get the features from the edge source node, slice the weight tensor, and then store the results in the edge element. We proposed linear operator reordering as an optimization at the inter-operator level to reduce the computation complexity and intermediate data size. Originally, the number of multiply is nkq plus nq. By reordering the computation, we bring down the n factor to k in the second term. The intermediate data size is brought down similarly. Next, we are to show how intra-operator level IR helps eliminate redundant weight copies and enable compile materialization. The edge message generation in an RGAT layer can be effectively done by a gem kernel. It contains 3 steps. First, it will gather the source node feature according to the source node index array. Second, it does the gem computation. And third, it scatters results according to the edge index. As we generate the kernels with custom access scheme, we keep only 1 copy of weights and load the right matrix from it during the matrix multiply, therefore eliminating redundant weight copy caused by lack of TensorView in PyTorch. Another optimization is compact materialization. It eliminates redundant computation and memory footprint. We notice that some of the computation are repetitive. The edge message is dependent only on the source node and the edge type. For example, if an author writes multiple papers, then the messages on these edges are identical. To leverage that, the output tensor will have a different layout. Originally, the output tensor has edge feature in each of its rows, but now each row has a feature corresponding to a unique pair of node and edge type. This change is reflected in the layout choices when lowering it to the intra-operator level. The getter list of the input matrix X and the scatter list of the output matrix Y are changed accordingly. When it comes to succeeding kernels, the change in the layouts will be reflected, and during the lowering, the kernel getter scheme will change correspondingly. We evaluate our Hector system on a single GPU machine. The heterogeneous graphs are provided by TGL and OGB. Comparing the most optimized Hector code with the existing systems, Hector's performance is consistently better. Hector is more memory efficient in that it does not trigger any out-of-memory errors, while existing systems do trigger out-of-memories in larger graphs. To show how Hector mitigates the memory intensiveness, we go back to the inference breakdown and compile Graphiler's performance with Hector's. We zoom in part of the figure. As shown, Hector has almost non-indexing or copying operations as it's free from tensor data movements. It does have a little bit of transfer from the host sides to the device sides to pass the metadata that specifies the block assignment. Additionally, it has larger ratio of matrix multiply to other compute. To summarize, we identified two RGNN performance challenges. To systematically address them, we present the Hector IR and code generator framework for end-to-end RGNN training and inference. Through elimination of redundant weight copies and efficient tensor materialization, Hector effectively mitigates the out-of-memory errors. Hector outperforms existing systems and delivers two further optimizations. Thank you for listening.
Any questions? All right, so nice talk. So actually, I want to ask a question. So you actually have a rich set of optimizations here on Hector framework. Like you mentioned, the operator reordering to reduce redundancy, and you have data layout optimization, and kernel fusion to reduce the launch kernel launch overhead, and so forth. So according to all these optimizations, so in your final results, if I look at breakdown, so which part actually contributed the most? Let's say out of 100% improvement, you got like 70% from, for example, layout optimization or something. I'm just curious on that.
Yeah, that's actually a very good point. So actually in our evaluation, we have a more detailed breakdown showing like how the optimized Hector code compared with unoptimized ones. So actually one of the arguments we made in the paper is that this, like the best optimization strategy actually depends on the input because this is a data dependent operations. So people like who are interested in this are invited to read our papers to learn more about the breakdown. But yeah, thanks for the question. Thank you.
Prashant Dattatreya, Microsoft Research. If I understand right, all the models that you are evaluating are without sampling, right? So when you say RGCN, you're not using sampling, you're doing no sampling.
Yeah, exactly. We were doing full graph training. Yeah, exactly.
Yeah. So what are your thoughts on extending this to sampling?
Yeah, that's actually a very good point. So we taking like the node features as a big tensor. So when extend to a sampling-based method like graph stage, we can take in a tensor. Now it's a subgraph like after the sampling. So the technique like the optimization and code generation techniques we propose still apply there. But we now like in every iteration we take in like a tensor of subgraph rather than the whole graph. And there we like the code gen, the optimize we can still get like optimization we get, but like it's just like for every iteration now we need to pre-process and get that like node feature tensor before like input into the kernels we generate. So it still applies there, but yeah.
Yeah, thank you. That makes sense. Thank you.
Any more questions?
It is a follow-up question. When you do random sampling, as the name suggests, it's random, right? So you don't know which nodes will you grab beforehand. Does this still apply? Do you do like on the fly code generation to handle that, or you generate the code just once and then just repeat? In the second case, the random sampling doesn't handle, it cannot be handled.
So right now all our kernels are generated ahead of time, so we use them like if like in the future it's extended to like sampling based method, we will reuse the same kernels and the compiled binaries. But as we mentioned, like we figured out that there's no one size fits all optimization strategy. So those subgraphs may have different properties. So there might be some like interesting runtime decision making to figure out like how to choose like different kernel versions. But yeah.
Are you planning to work on this?
Mm-hmm.
Are you planning to work on this next?
That would be in future work, yeah.
All right, let's thank our speaker again. So our last presentation is from Yufeng. Yufeng is a software engineer from the System Research Group at Google. His research interests focus on microservices and machine learning for systems. Recently, he's also interested in efficient large language models serving systems. He has received several macro topics in the journey of his PhD. And prior to Google, he was also a software engineering at Alibaba Cloud, working on its AI operations. And he received his PhD from Cornell University.
Right. Yeah. Thank you. And I guess I'm the last person to prevent you going to the happy hour. And all right. So my name is Yu, and I'm here to present my work like from Alibaba in 2 years ago. And it is different from the previous papers. It is actually a application of graph neural networks to solve some practical problems in the cloud. All right. Root cause analysis of microservice system is actually a very important topic. And so for people is not familiar with microservices. So microservices, it is a collection of independently deployable services that are loosely coupled, and they can collaboratively serve the user's request. And microservices is a very popular it's a very popular software design pattern, and it is vast adopted in the cloud. And distributed tracing is a very powerful tool to monitor the request behaviors across different services. And from this graph, it is a very simple distributed trace for a very simple microservice. And the length, so it contains different spans, and each span it represents a execution in of that request in a service, and the length of the span is basically represent the latency. And the target of root cause analysis is basically to locate which service is the root cause that originate the performance issues for the SLO violations, such as the tail latency violation or the request errors. And in this paper, we basically solve this problem with graph neural network, and we have 3 major contributions. The first, we propose a GNN-based model that is super scalable compared to previous models for the microservice root cause analysis. And second, we propose a really lightweight similarity metric to cluster the traces so that we don't have to spend repetitive time to infer to do this analysis for every trace. And third, we propose a evaluation methodology to generate the production scale microservice, so that we can do a realistic benchmarking of all AI ops algorithms. All right. So why do we want to propose or want to use that super complex graph neural network to solve this problem? It is because microservice performance debugging is actually very, very challenging. So first of all, microservices have a really complex dependency graph. The bottom two graph actually shows the microservice call graph from Twitter and Uber. And they are super complex for SREs to figure out the issues inside, especially when the performance issues can propagate along the dependency graph. That can make the performance debugging more difficult. And yeah, as I said, it's really hard for SREs to handle this problem dynamically and figure out the root cause in a very short time. And second, we figured out that some empirical rules that the SREs they are using very, very often is actually no longer applicable at a larger scale because of this increased nonlinearity when the scale grows. And also, it's very hard to disentangle the causal relationships between different downstreaming services. So here I show just two simple examples. The first example, we observe that the accuracy of N sigma rule, which is a very, very popular rule commonly used in production for SREs to figure out the root cause, it actually fails when the number of services increase. And in the graph at the bottom, we observe that there's almost no linear correlation between the parent and child and the child RPCs when the systems grow in size. But actually, they should have some causal relationship. It's just this relationship is super nonlinear, and that's why we cannot observe in this correlation plot. And the existing microservice benchmarks, they have a lot of limitations, basically because they are very compared to the production systems, they are very small, and they are not comparable with the scale of the production service, and that's why some of the issues in the proposed method we cannot observe them. And so basically to solve this challenging problem, we propose a GNN-based model for microservice trace RCA. And so it's very similar. So the core idea is very similar to my previous project at Cornell, which is Sage. So in Sage, we basically model the RPC. We basically model the RPC latency and the error propagation using causal Bayesian network because we observed that they propagate in a way that's similar to message passing, and it can pass along the RPC dependency graph. And therefore we can easily use the causal Bayesian network, and we can easily build the causal Bayesian network from the RPC call graph. And second, similar to Sage, we basically run iterative counterfactual queries to locate the root cause service of the performance issue, and it basically asks what the latency or the error status of the end-to-end service will be if the service X had been normal. And the service that counterfactually resolve the problem is the root cause of the issue. But in real life, it's very challenging to run the real counterfactual experiments in the cloud. And therefore we need to simulate therefore we need to basically simulate the counterfactual queries with GNNs by predicting the parent RPC status with the child RPCs, and that can be simply achieved by node level prediction. And there are two reasons why we use GNN models. So first, GNN model is highly efficient to model these nonlinear relationships in a high-dimensional space. And second, unlike Sage, we can just use a single GNN model for all the microservice topologies, and therefore we can actually. So if we have a lot of microservice systems, we actually can pre-train our model with the previously observed microservices, and then infer it on a new service with zero or with just a little or even no fine tuning at all. So here we for our model we collect several node level features, and it basically contains all of the information that we need for a span. And because of the time, I will not go into the detail. And because we use the Bayesian network, in terms of the network architecture that we use for the latency or error prediction, we basically can just use one layer of graph neural network to model the message passing within just one hop, and it basically it simply just follow the causal network formulation. And instead of predicting the parent latency directly, we actually predict the latency contribution of a child RPC to the critical path. And then we aggregate those latency in order to and we add those latency and also the exclusive latency, which is the parent's latency without waiting for any other children latency. We use them to simply predict the parent latency under some intervention when we do the counterfactual analysis. And we observe that it generalizes better and to some out of distribution data in the validation set. And because there's a huge number of traces that we collect in the production clusters, and the trace can have very similar patterns when the performance issue happen. So we use the trace clustering to help to reduce the inference cost because we don't want to run the causal inference every time for every trace. So I will. Because of time, I don't want to go through the detailed mechanism. And the basic idea is basically we convert the trace graph into some weighted sets, and we convert the measuring the similarity of the graph to the similarity of some weighted sets with jacket indexes, and then we use this as distance metrics to measure the similarity of the traces, and use a hierarchical DB scan for clustering them. And later when we do the inference, we only need to run the analysis for the centroid of the cluster. And finally, because the production scale system is very large, and we are in lack of the large scale benchmark to generate the arbitrary to measure the performance. We use the methodology to generate the microservice benchmark that can be arbitrarily large. And the methodology is pretty simple. So first, the users can input some configuration that defines the number of services and RPCs. And then we generate some random RPC call graph for every call paths to those microservice systems. And we also generate some random graph to represent the execution dependency graph if there are some large fan out from the parent service. And then we use some synthetic RPC handler generator to generate some execution kernels. For example, the CPU kernels, the network IO kernels, or context switch kernels. And finally, we use those generated configurations to generate the microservice based on some microservice framework, for example, gRPC. And in this way, we can actually emulate the microservice in a very large production environment. We can support Kubernetes deployment and cloud tracing and cloud logging, and also we can inject a number of faults via some open source chaos engineering tool. And finally, here comes to our evaluation. We evaluate our model with two small scale open source microservice benchmarks, and also we evaluate our model with our synthetically generate microservices from four services to 256 services and 1,000 around like 1,000 RPCs, and those are a very very huge scale microservices, even compared to the large scale production deployment. And we compare our methods with some heuristic-based methods and also learning-based methods with simple models like linear regression and also complex model as Sage. And finally, we use chaos engineering tool that I mentioned before to generate the ground truths for evaluation and also training. And so first of all, let's look at the root cause analysis accuracy. So our method, it actually outperforms the existing work, especially at a larger scale. And second, compared to the method that directly predict the latency, actually the indirect prediction, it has better generalizability, and that's why it can have a better accuracy. And finally, we observe around 10% accuracy drop with clustering because some clustering it basically miscluster the traces with different root causes in the same large cluster. Yeah, and finally, we also have some numbers for training and inference time, and our observation shows that the GNN-based model, it has better performance in terms of training and also inference. All right. So finally, we in this talk we present Sage, a graph neural net based root cause analysis system. We evaluate on the accuracy and also performance, and we have other evaluations, for example, the flexibility of the model and also generalizability of the model, and those evaluations in the paper. And also finally, we have some great impact in both the company and also the research community. Right, thanks.
Questions, only one question. Oh, okay, I'll be very quick. So for microservices in cloud, it changes over time. So if you pre-train the model, probably need fine tuning for that to adapt it to the time sensitivity. And what's the overhead, or do you consider the overhead for fine tuning everything?
Yeah, so actually so if the microservice just change a little bit, so actually we can fine tune the model very, very fast. We can actually, we show in the paper that like with like hundreds of samples, we can actually fine tune the model. But if the model changes in a larger scale, maybe you need more samples to fine tune that.
Yeah, thank you. So let's thank all our speakers. Right. And thank you for your attendance. So wish you all a happy hour in the banquet. So bus is outside.